לא פרקתי. יש שני מאמרים. Let's be there. Okay, so I'm happy to introduce Dana Moshkovitz from UT Austin, and she will tell us about encoding and decoding code in small time and space. Thank you.
Okay, thank you, Noga. Thank you for inviting me. Okay, so I'm going to talk to you about coding theory in almost linear time and sublinear space. This is based on two joint works with my student, Joshua Cook. So, right, let's talk a bit about algorithmic coding theory, right? So classic coding theory asks for a code, you have k bits of message, and you're trying to, you encode them with n bits of code word, and you want constant rate, and you want constant relative distance. And then came theoretical computer science and said, you know, that's great, but we also care about the complexity of encoding and decoding. So we care about what's the time that it takes to compute C, to encode, what's the time that it takes to decode. So I give you a corrupted code word, and I ask you to output the message, how much time it takes, or how much, right, the complexity. And the first thing that people in our community looked at was the time, right? So initially the question was, can you do it in polynomial time? And then once we could do it in polynomial time, the question was, can we go to the minimum time, which is linear? And then by now we have good codes with linear time encoding and decoding. And this talk is going to ask, what about the space complexity? So suppose that you know, we still want good time for encoding and decoding, but we also want good space. And just like with time, also with space, there is a whole spectrum. So if we want small space, maybe we want space n to the epsilon, or maybe n to the law of 1, or maybe, you know, some specific polylog n, and ultimately maybe we want log n. But for now, for the sake of this talk, for me, good time will be n to the 1 plus law of 1. Good space will be n to the law of 1. Okay. Good. What I like about this question, you know, other than it's completely natural, it has lots of interesting connections to complexity theory. I'm going to show you one such connection today. This whole project started because a year ago, I got an email from Ryan Williams, and he asked me, do you know if there is a PCP in small time and space? And before we can even tackle this problem, the first question to ask is whether we have coding theory in low time and space. And this is how we start. Okay. So what do we do? So we have two papers. One of the papers has been on the ECC for a few months. The second paper is not yet on the ECC, but will be in a few weeks, hopefully. So the first paper was about encoding. So we have a code, asymptotically good code with deterministic encoding. That's time n to the 1 plus law of 1, and space but logarithmic. As is in the current version, it's written with polylogarithmic space. Josh promises me that it will be logarithmic space in the next version. And we do that with using unique neighbor expanders in a different way than the way that they're usually used. And we also have a lower bound. For this construction, it's really important that you have random access to your input. And if you don't have random access, not just if you have string access, but really in a very strong sense, even if you have like n to the epsilon different heads on the input that you can manipulate, even then you cannot get an asymptotically good code. So we have this upper bound and lower bound. So this is the first paper. And then the second paper talks about how to do decoding. So there is an asymptotically good error correcting code with deterministic decoding in almost linear time and sublinear space. And this is like from completely different techniques. Right, so this is locally correctable codes and a new derandomization. Yeah.
Just to clarify, these are both deterministic constructions of the codes as well? Like the codes are explicitly given?
Yes. Explicit codes.
And these are not the same code.
Yes, and these are not, it's not the same code. So it's two extremely different papers, extremely different sets of ideas. To the best of our knowledge, the first code with the good encoding, we don't know how to get good decoding for it. The second codes with good decoding, we don't know how to get good encoding for it. It's still open. I think that this is the next big challenge, to get a code that simultaneously time and space efficiently encoded and decoded. Hopefully, you'll see some of the challenges in that.
And this time is all in the RAM model? Like, is it also in the circuit model? Can you replace
let's talk about the RAM model.
Okay, but if you wanted to replace time by size, is this a feature of the construction, or?
Which of them also? I think that the first one should be also circuit. I mean, okay, I need to check offline, right? I think that the first one is probably also a circuit, and the second one is maybe more like a branching program type. Anyway, but I mean, I'm going to show you. So there are two papers with all kinds of ideas, and I had to decide what I'll show you in the not much time that I have. And what I decided was to only show you the second result, though if anyone asks me if there is time, I can also show you the coding. Maybe the main reason I wanted to show you the second result is that it centers around this idea, a technical idea that's really new and really different, and I think that it should be really useful beyond the scope of this paper, and I kind of want to share it with everyone, and I feel like that it's simple enough that I can actually show you in the time that we have. I want to mention one thing, the decoding that we have, so I'm going to show you a non-uniform decoding algorithm. You're going to see very soon exactly how I use the non-uniformity. The non-uniformity is not essential in the sense that there is a very small gap between what we have and a uniform construction. I'm going, if I have time, I'll show you exactly what's the gap. You basically need to solve known problems about samplers, get better parameters than what current techniques give you, but only like by a little. So I kind of feel like the non-uniform will go away at some point in the foreseeable future. But it's really useful for educational purposes, because when I shoot only for non-uniform decoders, I can actually disentangle two different issues and just focus on one very clean thing. So hopefully you'll see that it's a nice formalism. Yeah.
The second result doesn't fall from like not the decodable.
We'll talk about this. We'll talk about this. Because the short answer is that they give you randomized decoding, not deterministic decoding. This is exactly the point. We'll talk about this. Okay? More questions before I start? I haven't started yet.
Will you talk about like related works, like AC0 decoding and things like this? Because this also is slightly related.
Yeah, so there was the only relevant related work that we found was constant depth coding theory, and there is some relation. At least this has some relation. Like after we finished this, after we did this, we realized that similar ideas were used in constant depth. What turned out to happen is that they had a non-explicit construction. We have an explicit construction, so you can view our contribution as at least in the upper bound, doing it explicitly, which I mean was not right. We had to work. Okay, more questions. Okay, so let's do it. Okay, so Klim pointed out that locally decodable codes should solve the time-space efficient decoding problem. So let's talk about this. So locally decodable code, so right, we encode some message and we can decode any single index by looking at only a small number of the small fraction of the, not fraction, a small number of queries in the corrupted code. Okay, and by now we have tons of work about locally decodable codes, and we even have asymptotically good codes with n to the layer 1 queries. What?
The codes you could stack.
Yes.
Okay.
Right, is in constant rate, constant relative distance.
Okay.
But you will see that what we, okay, you'll see exactly what happens. Right, it's thanks to you. Anyway, so this is known, and this immediately gives you codes that are time space efficiently randomized decodable. Okay, why is this? So usually when we talk about locally decodable codes, we only care about decoding a single index, and we say we want to succeed with probability 2/3. But now we're talking about global decoding, so we don't want to decode just one index. We want to decode, k indices. Okay, so we just need to get the error probability sufficiently below 1/k. Really, but we can do it. We can do it with repetitions as long as you repeat like log k times. It just makes the number of queries you add like a factor, like logarithmic factor here, which is nothing, right? Because this is the number of queries we're talking about. And you get the probability sufficiently small, and now you actually decode the whole thing. Okay? Good. And this is inherently randomized. And this lets you decode globally in time. Well, you just need to go index by index. There are about n indices, and k is order n. And for each one is only do n to the layer of 1 time. And also the space, you really do computation on the number of queries. Okay? So locally decodable codes immediately give you randomized decoding. Okay. Let me mention, you can also consider the very related question of correction instead of decoding. Correction is I give you a corrupted code word, and you don't want just to figure out what's a message, but we want to figure out what's a code word. And then you just use locally correctable codes, which we also have with those parts. Okay. Again, thanks to Noga and Swastik and Or and Shubangi. Okay? Good. By the way, whenever people have questions, please raise your hand and ask. Okay? Okay. But I don't want randomized decoding. I want deterministic decoding. You'll see very soon why I insist on deterministic, some of the motivation for insisting on deterministic decoding. And what you get if you want to do deterministic decoding is you get quadratic time instead of almost quadratic instead of almost linear. Okay, so let's talk about it. And also this will give you, you'll find out why I insist on talking about uniform decoder, non-uniform decoders rather than uniform decoders, how this is a very useful simplification.
So another question, if you were to compromise on the rate, say 1/polylog, then this would be fine. Then this approach would give you
So you haven't seen yet, I haven't told you yet what we're doing, but what I'll...
No, just the old approach. The old approach, you said it would require quadratic time, just because you insist on concentrate. You're using locally decodable code.
No. The quadratic time is completely inherent. It's not about the rate. What you can get if you compromise for the rate is the n to the layer of 1 can be much smaller, can be polylogarithmic. Okay? So instead of getting the n to the layer of 1, you'll get polylog n. Okay, this is great, right? If you care about this, this is absolutely awesome. Yes. This is where I was. Inherently, completely inherently, the time is quadratic. So let's go through it. So recall, the input is a corrupted code word. The number of possible corrupted code words is some exponential in n. Okay, this means that you only need order n randomness strings in order to corrupt every code word. Then for every corrupted code word, 2/3 of the randomness strings are good. So now just pick from all the randomness strings, pick order n uniformly at random. Okay, so the probability that you're not decoding well for some corrupted code word with all the order n randomness strings is exponentially small in n. If you take the exponentially small, sufficiently small with respect to the number of inputs, right? This is the Adelman trick of derandomization, right? This is a Chernoff type calculation. Only order n randomness strings suffice to correct for any possible code word. Okay, and what I'm going to do in this talk, because I'm only shooting for uniform decoders, I'm going to assume that I have access to this order n good randomness strings. Okay, and if we want later a uniform decoder, fine. I just need to figure out for the code what are the good order n good strings, which is often very possible. But for now, all I care about is that there are only order n randomness strings, and necessarily I need order n randomness strings, right? This is just the number of possible randomness strings that I should consider. Okay, is this calculation, is this argument, are people fine with this? What? The length of, the number of randomness.
The length of each random string. This is the number of random strings. Do you care?
I don't care, but right, what I care about is that I can.
It's advice. It's not like memory.
Yeah, it's advice, right?
You kind of store it somewhere. You don't store it. It's an advice.
Right. This is my advice. Those randomness strings.
When you make it uniform, you need to store it somewhere.
Yes.
You carry it into the letter of 1.
Yes, but also it's not a problem. It is indeed n to the layer of 1. Okay, good. So this is like an extremely important point that you need order n strings. Order n strings are sufficient and necessary. Okay, so now if you want a deterministic decoder, what you can do is go through all those possible randomness strings and then check each, and right, but then the space is quadratic, the time is quadratic, right? Because you go through n things, and for each one you need to test it in time n. So necessarily, completely, it's quadratic. Okay, this is an extremely important point for this talk. The space is small, but the time is terrible, and it looks basically impossible. Right, because you can't get around this. You have to have order n strings. You have to test each, and it takes order n. Right, it's quadratic. Okay. In 2006, there was a work that proved the lower bound. So at least for non-adaptive algorithms, like this one is non-adaptive because you always go through the same kind of computation, no matter what you see. For for any such algorithm, indeed, if you want almost linear time, then you need about linear space. So if you want small space, you need quadratic time. Okay, so there was basically a lower bound, but the lower bound was only for non-adaptive decoders. And the question that I asked Josh was, can we just lift the lower bound to work for all deterministic decoders? Okay, because the feeling is you really need quadratic time. You have n, you need to test each in n. Okay. Okay. So this is the question. I want to tell you what was my kind of motivation for. I really care a lot about this question, and what was my motivation. And this gives you one connection of this question to complexity theory. Okay. So this is about the power of randomness in computation. So Avi Vigdorson just won the Turing Award. One of his notable contributions to theoretical computer science was this proof that if you believe standard plausible complexity assumptions, then BPP equals P. Then randomness does not speed up computation beyond polynomials. And a few years ago, with David and Dean and Justin O, and then some follow-up works, we went back to this theorem and we asked, okay, so you start with randomized algorithm in time t. What's going to be the deterministic algorithm that you get? You know, assume whatever complexity assumptions, reasonable, true, probably true complexity assumptions you want. What's going to be the deterministic algorithm? And if you go back to this in Pagliazzo-Vigdorson and other works, there was so many works here, all of them completely inherently for a bunch of different reasons, had a huge polynomial blow-up. So what the polynomial blow-up was, you start with time t, and you get randomized, and you get deterministic time, I know, t to the 8, t to the 9, right? Crazy stuff. And I wanted to know the truth. And by now, at least more or less, right, it all depends on what assumptions you're happy with, but we know quantitatively what should be the truth. If you have time t space s randomized, then with pseudo-random generators, you can get time t times n in space s. Okay? And n is the input size. N is always the input size in this talk. Right, so randomness helps you by at most a linear factor. Okay, and the question is it tight? And the answer is, well, it's tight in certain situations. Most obviously for problems like local decoding or like property testing, right? In property testing, we can do things randomly in constant time or in n to the LR of 1 time. And we don't even look at the entire input. We look at only this tiny portion of the input. And for all those tasks, they are non-trivial and they require looking at all the input if you're trying to do them deterministically. So we have basically n versus 1 kind of separation between deterministic and randomized. So definitely for some t's, for t which is about 1, this is needed. But the question is it true only for property testing? Or is it true beyond that? And Ryan Williams had this one work where he showed like an n versus n squared separation. But the separation was under this assumption called NSEF. And the thing about NSEF, Ryan gives it 50% chance of being true. Okay, so Ryan doesn't believe this assumption. So it would be really nice to have like a more believable result. And I was really hoping that global decoding would be this thing. And it made a lot of sense to me, because if here there is a separation, all we need to do is to lift it to the corresponding like n versus n squared separation.
Is the distinction between Boolean functions or languages versus a long output matter?
It depends how long. It depends. Yeah, there are all kinds of. We can talk about this later. But yes, it does matter. But it's complex. There is a complex answer. Anyway, yeah. So I was hoping to get this. This would have been. I would have been so happy if we could prove this. And I was telling this to Josh, and Josh came back and he said no. Actually, there exists an asymptotically good error correcting code with almost linear time and sublinear space. Okay, there is no quadratic versus linear separation for this problem, even though in the locus version there is. Okay, so this is the main theorem. Okay. And the nice thing is not only we prove this theorem that's natural and nice and everything, but the proof goes through a new derandomization method. So what we do is we take any typical locally correctable code. I'll tell you what typical in a second. It's not very important. We take any typical locally correctable code. This corresponds to a randomized decoding. And we get from it a deterministic decoding with good complexity. Okay? And this is very unusual for derandomization methods. Most derandomization methods actually increase the time of the deterministic algorithm, definitely everything based on pseudo-random generators or something. There are very few methods that don't increase the time compared to the corresponding randomized algorithm. And I'll show you how this magic is done. Okay. Let me just briefly say what's typical. So we call locally correctable code typical if the corrector has perfect completeness and is non-adaptive and is smooth. So it queries every symbol with roughly the same probability, and also the encoding is systematic. Basically, all the constructions that we have are either like this or very easily can be adapted to this. So this is really nothing. We basically take any locally correctable code, anything that's known right now, and also anything that will be known in the future, because you guys will continue advancing this theory, and we can get from it a deterministic decoder.
Space is roughly number of queries.
What?
Space is roughly number of queries.
Yes, you'll see. Basically, I'm going to show you this essentially in full. Okay, so I have 15 minutes. I'll show you this in full. Okay, and it's one, in my opinion, a really awesome idea that should be widely known. Okay, so I don't want to spend too much time about uniform decoders. I wanted to comment that, say, if you take Reed-Muller, right, our quintessential locally correctable code, and you ask, what do I need to do to get it to be uniform, right? So you just need better curve samplers. Amnon and Zayu and Chris Humans have constructions of curve samplers. It's a well-known problem. You need to push the parameters slightly beyond what they could do. Let's not talk about it because I want to show you the big idea. Okay, but it's really getting a uniform decoder is really, I don't think that it's going to be like it's beyond what we know right now, but it's not in the sky. Okay. Okay. What I want to do now is show you the reason I want typical locally correctable codes. And the fact that the reason I want typical locally correctable codes, the thing I want out of it, is that typical locally correctable codes are actually locally testable codes, at least if you consider only words that are somewhat close to the code, right? So usually anyone who worked on locally testable codes knows that the difficult part is for words that could be extremely far from the code. So we're not dealing with this. We're only dealing with the case that locally correctable codes can deal with, which is you get a word that's corrupted, And you want to figure out roughly how corrupted it is, here up to a 2 approximation. And the thing is that you can do it with a typical locally correctable code. Why? Because you're going to correct a random index, and then you're going to compare to what you got. And it works. OK? And just like the same trick that we did before, the same kind of Chernoff-like argument, we only need order n randomness strings for this. And therefore, we get a non-uniform deterministic algorithm in almost linear time and space, and sublinear space. OK? So the testing problem, even like figuring out, getting an estimate on the distance, on the relative distance, this is, for those words, this is solved for typical locally correctable codes. OK? Hey, so everyone who worked on this is like nodding, yeah? OK. Hopefully anyone who has any question, wants me to clarify something or repeat something, just say. OK. So I wanna show you the new derandomization method. And we call it the iterative correction method. For a reason you'll see in a second. So iterative correction, right? This has been done in correction or decoding before. So you start with the corrupted code word that you got. So this is like those n bits, and there are some corruptions, let's say 0.1, a fraction of corruptions you don't know well. Okay. And all I'm going to try to do is to improve the number of corruptions. So if in the beginning, basically, I have order n corruptions, in the next step, what I want to get is n to the 1 minus alpha corruptions. Okay, and the corruptions could be corruptions that I had before, could be new corruptions that end up, but I just want fewer overall. Okay, this is my goal. And I'm going to repeat this, and in the next step, I'll want n to the 1 minus 2 alpha, and so on and so on. And after about 1 over alpha steps, right, the number of corruptions goes down below 1, meaning it's 0, and I'm done. Okay, so this is what I'll be doing. Okay. And now comes like the key observation, key thing that is going to make the whole thing work. I'm going to prove this to you in 2 slides. Okay, so this is coming. But it turns out that if all you want to do is to improve the number of corruptions by factor 1 over n to the alpha, right? So I'm not trying to improve right away everything. I want to improve slightly, right? Only this factor. It's actually enough to look at about n to the alpha, any about n to the alpha randomness strings among the order n that I have. Okay, I'm going to prove this to you. Okay, so if I only want to do to make small progress, I don't need to look at all the n possible randomness strings, only n to the alpha. This is what I'm claiming. Okay. And this is the key to get around this major quadratic obstacle that we had before. Because, so for each one, I'm going to look at n to the alpha randomness strings. Here n to the alpha, here n to the alpha, here n to the alpha, and so on and so on. Okay. So the number of randomness sequences, right, in the end, to go from like lots of corruptions to no corruptions, right, I need to choose randomness here and randomness here and randomness here and so on. The number of possibilities is about n to the alpha to the 1 over alpha, because I have 1 over alpha iterations. So the number of randomness strings that I'm going to look at is about order n. I knew that I needed order n randomness strings, right? And this is what I have here. But the point is that for each, in each iteration, I only need to go over n to the alpha randomness strings. For each one, I need to do an n time computation. So overall, it's n to the 1 plus alpha. And I need to do it 1 over alpha times, but 1 over alpha is tiny, right? So this is the dominating factor. Okay, so this is like the big idea by working gradually by having a very modest goal each time, I can actually circumvent this quadratic thing. Okay. I'll prove the key claim, but I want to just point out there is one more very important implementation issue here. So iterative decoding, we've seen it in many decoding algorithms, right? We saw it in Spielman codes. And those codes are definitely not space efficient. Why? Because if you want to do iterative decoding, you usually need to remember your current word, right? You started with the input, but each time you build this new word and new word and new word, and you need to remember them, and this takes the inner space, right? So potentially this could be very inefficient in terms of space, but in our case, it's actually very efficient. Why? Because we're not going to remember the whole word. We're not going to maintain this in memory. We're only going to remember the randomness that led to this. Okay, so we have something that represents, right? We chose in each step, we chose some randomness string, and we're going to remember what we chose. And whenever we need to query something, we're going to do it on the fly. Okay, so what it means is that the number, the time is going to be n to the 1 plus alpha, but also times the number of queries to the 1 over alpha. Right? If the number of queries is sufficiently small, this is going to be n to the layer of 1. Okay, and similarly here. Okay, so I'm doing computation on the fly. I'm not actually maintaining in memory the whole word, just the randomness that describes them. Okay? Let me prove to you the key claim. The key claim was that if you only want small progress, you only want to improve the number of corruptions by 1 over n to the alpha factor, then you only need to look at about n to the alpha randomness strings. Here is the proof. So for simplicity, let's consider the first case. There are order n corruptions, and I want n to the 1 minus alpha. Okay, and actually to get it for general number of corruptions, you need to be a bit, it's a bit more subtle, but you'll get the point already from this. So consider this table that in the rows has all the possible randomness strings, and in the columns has all possible symbols that I may try to correct. Okay, so here is an R and an I, and what I'm going to write in every slot is, did correction succeed when I had a randomness R and I try to correct I? Okay, so let's do the calculation. I did remember that I'm doing this whole thing, I'm doing this repetition. I got the error probability down to 1 over n. Okay, so this is a table of size order n squared, and the fraction of failures is only 1 over n, meaning that the total number of failures that I have, correction failures, in the entire table is only order n. Okay, this means that I cannot have much more than n to the alpha rows that contribute each one at least n to the 1 minus alpha failures, right? Because then I'll have more than n. So it means that if I look, right? So I'm done. I proved what I promised. This is it. Okay. This is it. So this shows this. Questions? I promised to do it on time, and I did it on time. Yes.
Why did the error probability start at 1 over n? Could it have been 1 over n squared?
No, but there is a correspondence between the error that you want and the number of randomness strings that you.
Right, so it was 1 over n squared.
So, I mean, you could have had like a smaller number of right. There is some trade-off between you just want, right? There is a trade-off between how many rows you look at and how many failures you have in each, and you want this to be larger than.
So, I don't understand. How do you assign, like, So you don't need to account for the time. It's like it's in the advice, right? Which end to the alpha witnesses or whatever are relevant to which.
No, but here this shows that I can look at any n to the alpha.
Any, okay.
Any, and they will be good.
And one of them will be.
One of them will be good, right? I'm going to go try all of them.
So you try all of them in the very beginning, and then you test.
And then I test each one.
And then you know which one did it.
Yes. And I fix this and I store the one that I.
And for that testing, you run this local correction algorithm.
Yes.
And that's de-randomized with.
Yes. Once you're talking about the non-uniform world, you don't worry about how exactly to do the derandomization. Yeah.
And you said something about the whole result is only a little non-uniform, or is it?
So what I said is that you can make the whole decoding uniform by figuring out what are the order n strings that you need to look at. And for Reed-Muller, the randomness strings, if you just look at curve samplers, they give you the right thing. But you need the parameters to be good enough, and with current constructions are not.
What would be the decoding?
You have a uniform decoder.
What?
Oh, what it would be?
Can you phrase it in the language of curve samplers? Suppose you have
For Reed-Muller. Yeah, so the possible randomness strings, each randomness chooses a curve in your space, and you just look at the curve, and the curve, right, the restriction to the curve should be a low-degree polynomial, and you just do the decoding in the low, right, of the low-degree polynomial, and right, this is how you correct.
The deterministic thing would be to choose a couple of good curves.
You choose n to the alpha, any n to the alpha, a bit more than n to the alpha among the curves that we have, and try all of them.
And this
And
would
see.
be deterministic decoding, assuming that the parameters are good enough.
Yes. And that will improve the distance from something to something small, and then we will do it.
And you will do it again and again.
You are going to do that process iteratively.
Yes. Right, this is the whole idea, is this iterative. It doesn't matter, but you're talking about completely different code words or corrupted code words in each time.
It is the same samplers?
You use the same family of curves.
But each time you choose different?
But each time, no, it doesn't matter what you choose, but each time you choose a different word. Right, each time you have a different word that you're working
That you
on.
reached.
The ones that you reached up to here.
What are you using here, adaptivity?
What?
What are you using here, adaptivity?
Because I'm checking which is the right randomness string.
So
This depends on the input, and then I go with it. So it's completely adaptive.
So the local testing is what is adaptive.
I mean, the whole approach, right? Testing just lets you choose which is the right one.
But the same curves will work for other polynomial codes, like multiplicity codes and stuff like that.
So I conjecture that yes, you maybe use a manifold rather than curve, but I mean, yeah, so this is the reason that the paper is not on the ECCC yet. We're trying to figure it out.
Okay.
Okay.
Yeah. Just to make sure I understand, did the local testing also require the non-uniformity?
Yeah, it's exactly the same reason as before, right? But curve samplers would give you that. Yeah. Okay.
More questions? Okay, let's thank you. Long glance, and then
Let me know. 5 minutes.